Okay. Last time we reviewed matrices. We will come back to matrices later also. But today I'll start with chapter 1, linear algebra without coordinates. First, before we introduce vector spaces and so on, we will start with something you are familiar with. So, chapter 1. Linear algebra without coordinates. Okay, now first topic we will see is so section maybe one vector spaces. And as a format, we will first consider three-dimensional Euclidean geometry. Basic questions of three-dimensional Euclidean geometry. This is you know probably from high school or the first few courses. Entry space. Okay. Whenever we have a point, we can, okay, consider this point as a vector like this, and suppose so this is the point, and this is the vector, and it has coordinates. Identify this with this triple, meaning that like, when we take its projection onto the xy plane, this is the point x comma 1, or maybe x comma y comma 0, z coordinate is 0. So this is x, this is y, and this is z. So this R is a vector, and we know how to do algebra with this, right? We have addition and addition and every multiplication. And product of vectors are kapanmış. So let me start again. Okay, so we will start studying vector spaces, and as a basic example, we recall three-dimensional geometry of vectors. Whenever we have a point in the space, we may join this point to the origin and we obtain so-called a vector. And for vectors, we have addition, scalar multiplication of a vector by a scalar and product of two vectors. Let's recall what they are. Addition. Now, whenever I have two vectors, how do we add them up? We just add corresponding coordinates, like x1, x2, y1, y2, and z1, z2. And geometrically, this corresponds to something like this. If you have, let's say, these two vectors like this, let's say this is R1 and this is the vector R2, R1 and R2. Geometrically, this operation corresponds to the following. You just take vector addition of these vectors out. You draw parallels to these vectors in the plane containing these two vectors, and then these parallels will meet at the point, and this vector here is the addition. Okay, R1 plus R. This is the geometric meaning. What about scalar multiplication? Well, if you have, let's say, a real number and R, let's say, okay, x, y, z, then we define C times R as what? You just multiply the entries of your vector by the scalar. So you get Cx, Cy, and Cz. Okay? And this geometrically corresponds to the following. Suppose this is your vector R. C times R, if C is positive, so if C is equal to 2, for example, then you just multiply this vector by 2. So this is 2R, okay, 2R. If it is, so CR will be something like this, CR. If C is positive, if C is negative, then it will point in the other direction. So, for example, minus 2 R, okay, is this way. The geometrically scalar product is this. You just keep the direction of your vector, but multiply its length by the scalar. And if the scalar is negative, then you go in the opposite direction. Okay. All right. What about product of vectors? We also call this cross product. It is also called the cross product. Of vectors. So if your two vectors R1 and R2, their cross product is another vector. Okay, this is another vector. And it is defined as follows. We write here I, J, K, and then write the vector R1, R1 coordinate of R1 here, X1, Y1, Z1, and X2, Y2, Z2. Then R1 cross R2 is the following vector. You take the determinant of this matrix, 3 by 3 matrix, as if these are just numbers, okay? So you get what? I times, I start with this one, I cross first row and first column, then take the determinant of the remaining 2 by 2 matrix. So this is Y1 times Z2 minus Y2 times Z1. And then J times across this one and this one. What is that? X1, Z2, Z2, X1. So this is X1, Z2, sorry. X1, Z2 minus X2, Z1. And then finally, K times. This time I cross this line, row and this column. What is left is this 2 by 2 matrix. And I write its determinant. So X1 times Y2 minus X2 times Y1. So R1 and R1 plus R2, this I means the first coordinate, right? RJK are the unit vectors in the direction of coordinate axis. I is this vector, so it corresponds to the point 1, 0, 0. J is this vector, 0, 1, 0, and K is this vector, which corresponds to 0, 0, 1. So R1 cross R2 then is nothing but the following. R1 cross R2. I is the coefficient of I is this, so it is Y1 Z2 minus Y2 Z1, and then I have minus sign here, so it is X2 Z1 minus X1 Z2, and then X1 Y2 minus X2 Y1. Cross product is this, okay? And it has a geometric meaning also. What's the geometric meaning of cross product? Sorry?
The vectors that perpendicular to both.
Yes. So if R1 and R2 are two vectors like this, R1 cross R2 is a third vector, and it is nothing but this vector here, R1 cross R2, and it is perpendicular, as your friend said, to both of these vectors, okay? Both of them. R1 and R2 doesn't have to be perpendicular to each other, but this cross product is perpendicular to both of them. And we may write it this way. So this is perpendicular to R1. R1 cross R2 is perpendicular to R2. This notation, we use it to say that, you know, these two vectors are perpendicular to each other. Okay. what else do I need to say? We have, okay, you may ask the following question. I mean, here I multiplied two vectors, right, and obtained the third vector. Is this possible in other dimensions? For example, dimension 2, 4, 5, 6, 7, right, or other direct dimensions. Unfortunately, this is the only one. I mean, in two dimensions, when one dimension, of course, we have real numbers, which is one dimensional, and we have product. In two dimensions, we have complex numbers. In R3, we have this with this geometric properties, but besides that, we don't have anything like this. We have some other kind of products in 4 dimensions. We have so-called quaternions. You can multiply them, and they have nice geometric properties also. We will see them, but you know, this product is something very special to the 3-dimensional Euclidean space. Okay. Of course, you may ask why you don't have, you know, something like this, for example, in 4 dimensions or in 5 dimensions. These are innocent looking like questions, but they are difficult questions actually. And they are solved, I mean, recently, this kind of questions only in, I guess, 60s. So what I mean recently, of course, 60 years ago, but compared to, you know, long history of mathematics, since, you know, Egyptians, ancient Egyptians or Chinese or Greek mathematicians, you know, 60 years is something very recent. Okay. Şöyle yazayım onu, remark olarak. Cross product is something special for 3-dimensional Euclidean space. Actually, why do we say Euclidean space? Because this is not just R3, it's R3, but we have also the notion of length of vectors. So that's the next thing I will talk about. We have so-called inner product of 2 vectors. What's that? If we have 2 vectors, R1 and R2, their inner product is defined this way: x1, y1, z1, inner product x2, y2, z2, and this is what x1, x2, y1, y2, z1, z2. Okay. And in particular, R1 dot product with R1, that's x1 squared, y1 squared, z1 squared. And of course, this is nothing but length of R squared. Length of R is just the square root of this. And why is that? If you have a vector like this, vector R, and okay, so x, y, z coordinates. So suppose this is the x, y, and z. What is the length of this vector? Well, I can compute it as follows. I have this vector here. What is the length of this? Well, this is a right triangle. Çok yaşa. And this is the hypotenuse, and the length here is just x squared plus y squared square root. And then I have, belki şunu şöyle çizmem lazım değil mi? Şöyle. Okay. Another right triangle here. And this length is z. This is the hypotenuse. So length of r squared. Hypotenuse is what? This side squared, which is x squared plus y squared, plus height squared, z squared. So length of r, the vector r, so this length is this, is just x squared plus y squared plus z squared, and then we take square root, right? Okay, this is inner product. Inner product exists in all dimensions. Okay, it is nothing special to R3, unlike this one. We will study all these things in more detail later. We just see this stuff right now to get a feeling of what's the vector space and what's the vector and so on. Okay. Soru aklınıza bir şey takılırsa hemen sorun. Maybe before I pass to that, let me also tell you the following. There is one more geometric meaning of this cross product. Namely, if you form the parallelogram by drawing parallel lines to these vectors, okay, so you get a parallelogram here. The area of this is nothing but the length of this vector, R1 cross R2. Okay, so it is another geometric meaning of cross product. Length of this parallelogram is area of this parallelogram is the length of this vector. Okay. All right. We have also the following properties for cross product and dot product or scalar product. For example, this is also equal to the following: length of R1 times length of R2 times cosine of the angle between these two vectors. So if you have these two vectors here, R1 and R2, and if the angle is between them, if the angle between them is theta, then R1 dot product R2 is this. And we have something similar for cross product. The length of this vector is R1, R2, but this time we have sine theta. Okay. All right. Sorry? Yeah. I mean, how would you find the area of this gadget, right? So this is the area of this parallelogram. How would you find the area? Base length times height, right? This height. What is height? Height is just Okay, now sine theta is just theta, it is h over r2, so r2 is just what? Plus the h, pardon, h ve tamam, sinüs h şeye eşit, h over r2. Yeah, h is just, okay, h is just r2 times sine theta. And what is the area? This is just the area, right? Area is just base length r1 times the height, but height is just r2 times sine theta. Buydu değil mi senin sorun? Okay. Okay, thank you. Okay. Yok. Inner product actually exists in all dimensions. Let me write as an unlike cross product, inner product exists in all dimensions. Let me write this in quotation. For example, in Rn, if you have two vectors, let's say R1, let's say x1, x2, xn, R2 is another vector, let's say y1, y2, yn. We will define the inner product just as in this case. So we multiply corresponding coordinates and add them up. X1, y1, x2, y2, and so x and y. Okay. So inner product exists in all dimensions, but cross product doesn't. Okay. It is something special to R3. Okay. Well, this way actually we kind of introduced vectors in Rn also, right? So we have vectors in R2, in R3, but even if we cannot draw realistic pictures for Rn, almost all the stuff which works for R3 works also in Rn, except the cross product. But cross product will not be actually part of the definition of the vector space. So that's why that's not something very crucial, that we don't have cross product in Rn, because in the definition of vector space, we will not need cross product anyway. Okay, what we will need is scalars. Abstract number fields, let's say numbers and number fields. What are they? In R3 or Rn, our number field is just the set of the field of real numbers. However, as we will see, one may consider other kinds of fields. Okay, for Rn, we use real numbers as the number field. However, there are several other number fields. Okay, which naturally appear in linear algebra. For example, examples. So, of course, real numbers. We will use also complex numbers. Of course, sometimes we will stick to rational numbers. And there are other fields. And then we have finite fields. Finite fields. Okay, let me and extensions of these. Extensions what about this. Now I will both describe these in more detail and also write down mathematically what the number of fields. Okay. Let me first write down the definition. Onu da açıklamadım zaten şey. We have this, for example, real numbers, complex numbers, rational numbers, and finite fields. For example, finite fields have Z2 or other prime fields like ZP. And this is extensions of this. I will explain what this is. Actually, it's a one semester course, extensions of fields. But I'll just give some examples. That's it. Okay. But first, let's see what's a number field or simple field. The number field or simply a field. In high school, you probably have seen like groups, rings, and fields, right? No? In 160, okay. a number field is what? Is a set X which is an abelian group. So it is an addition operation, a commutative operation with respect to addition and the multiplication such that the operations addition, subtraction, multiplication, and division are defined such that addition is commutative. A plus B is equal to A. Multiplication is commutative. And 0 is the additive identity element. 0 times A is A. And 0 times A is 0, and 1 times A is just A. Okay. Inverse of an additive inverse of an element is denoted by minus A. So minus A plus A. So this is the additive inverse of this. Therefore, if I add additive inverse of a number to itself, then you get the identity element of that operation. Identity element for addition is just 0. Okay. And any element other than 0 has multiplicative inverse in a field. So A times I have so-called 1 over 8 in that field, and this is just 1. So any element other than 0 should have an inverse. So a field is basically this. Okay, you have two operations. Both operations are commutative. Addition and multiplication, and of course they have also these operations are çarpmanın toplama üzerine dağılma özelliği falan var mı? Var değil mi? Bunlar. Okay. Now let's see some examples in more detail. Maybe into non-example. Integers with addition and multiplication, usual addition and multiplication. Okay. Satisfies almost all the properties except that we don't have this one, right? An integer other than 0 doesn't necessarily have a multiplicative inverse, right? So it's a ring, but not a field. Since let's say almost no integer has multiplicative inverse. In particular, 2 has no inverse. Since 2, okay, this is different than 0, has no multiplicative inverse. For a number field, we should have multiplicative inverse. Okay. Reel sayıları, rasyonel sayıları biliyoruz. Kompleks sayıları biliyoruz. What are complex numbers? A complex number is a pair of real numbers. You can write it this way, or we actually prefer writing it this way. A times IB, where A and B are real numbers. The complex numbers are paired like this, and they form the fields. How do you multiply two complex numbers? You multiply them as if they are real numbers, but you keep in mind that I is a number, so that its square is -1. Okay, and then the rest is easy. For example, 2 plus 3 plus 2i, 1 minus I. What is the product of this? Well, 3, and then minus 3i, plus 2i, and then plus 2i squared, right? Because I have I here, another I here. So maybe I should have minus, right? There is minus sign here. So what is this? 3 minus 3i plus 2i. I squared is -1, so -2 plus -2 times -1 is just +2. So this is just 5 minus I. Okay, and how do you find the additive inverse? Sorry, multiplicative inverse. For example, what is 1 over A plus IB? Okay, well, it is just okay, A minus IB divided by A squared plus B squared. Why is that? Well, just, you can not so. Okay, so A plus IB times A minus IB divided by A squared plus B squared is what? So this is just a real number, and here you have A squared, and then minus I AB plus IB AB, and then we have I squared minus I squared B squared. Yeah, okay. And this, and these are cancelled, and here I have minus I squared. Minus I squared is just +1, so we get A squared plus B squared divided by A squared plus B squared. So this is equal to 1. Therefore, multiplicative inverse of this number is just this, because their product is equal to 1. Really? Peki. Extension'la etmiştim. So let me explain what I meant by extending a field. As I said, there's a huge topic, extensions, field extensions in general, but I'll just give you some examples. Field extensions, examples that field extensions. what you do, you take a field and then take a polynomial which doesn't have a root in that field, and then you just add the root of that field, that polynomial to that field, and you get something bigger. And that's how we obtain actually field extensions. For example, consider the field of rational numbers and consider this polynomial x squared minus 2. This has no roots in this field, right? Has no solutions or roots. In real numbers, of course it does, right? It's square root of 2. So what you do to get an extension of this, you take that root of this polynomial and add to rational numbers. What we mean by this is the following. I take rational numbers and then some other rational numbers and then add things like this. Similar to what we have done over here. Okay, here we actually did the same thing. Obtaining complex numbers from real numbers is the same idea. You add a root of a polynomial which doesn't have a root in real numbers. What is that? X squared plus 1 is equal to 0, right? X squared plus 1 is equal to 0 has no solutions in real numbers. We take a solution of that. In an abstract manner, you will see it in 367, how you obtain that solution. And then you put it in real numbers and you obtain a bigger field which contains the root of that polynomial. In that case, it is complex numbers. In this case, it is this case. So A and B are just complex numbers, rational numbers. So this is an extension, right? This is this is a bigger field containing Q. That's why we call it, it's an extension. It is called an extension of Q. Okay. How do we do arithmetic here? How do we multiply, add, and so on? This kind of numbers. Well, they are actually real numbers. We just add them as if we are adding real numbers. So, for example, how do we add this to elements? Similar to what we had done for complex numbers, you add this to A1 plus A2, and then B1 plus B2 square root of 2. Okay. How do we multiply? Let me just do one example like this. Yani aslında reel sayıları çarpıyorum. So this is 3 plus 15 root 2 minus root 2 plus 5 times root 2 squared. Root 2 squared is just 2. So this is 10. So this is 13 plus 15 times root 2. Okay. Efendim? Ha, şurada var. 14 oldu. Yok, nedir o?
Hocam artı 7 eksileş.
Şimdi şurası 3, şurası 15, kök 2, eksi kök 2, eksi 5. Şurası eksi 5. Şurası da bu 2, 10 oldu. Ama eksi 10, eksi 7 mi? eksi 7 minus 7 plus 14 root 3. Tamam mı? So this is another field, okay? It is not rational numbers, it is not real numbers, it is something between them. It contains rational numbers and it is contained in real numbers. You may wonder why things like this are interesting. Well, you should ask that to people who are studying number theory. Their life is this kind of things. And they're actually integer parts. So they are important in number theory, this kind of objects. Okay. What about finite fields? Let me also talk about finite fields and their extensions. The simplest finite field is this one, Z2, or maybe the people prefer this F2. It has only two elements, 0 and 1, and you know how to add or multiply these two, right? The only non-trivial one is this one. 1 plus 1 is 2, but in F2, 2 is the same as 0. Okay? So 1 plus 1 is 0 in this field. It has only two elements, 0 and 1. And it satisfies all that properties. So it's a perfect and nice field. And it has only two elements. This is definition, 1 plus 1. So this is a field of two numbers. Addition is, 0 plus 1 is of course 1. 0 plus 0 is 0. I have to just tell you what is 1 plus 1. 1 plus 1 is defined to be 0 in Z. Okay. Another one filled with, so this is actually modular arithmetic, right? You are doing arithmetic in mode 2. This is F3 or let's say F5. So there's 0, 1, 2, 3, 4. How do you add two elements? For example, 2 plus 3 is 5, but 5 is just modulo 5 is 0, right? 3 plus 4 is just 7. 7 is the same as 2. Okay. What about multiplication? For example, 2 times 3, it is 6 modulo 1, it is just 1. Okay. So this is modular arithmetic in mode 5. This is mode 2. What about efendim? Ara verebilir miyiz? Veririz. Okay, let's have a break. 10-minute break.